What? Okay. What's that? Well, what is negative 4 times negative 25? Positive 100. And then the minus 4 times positive 100 makes minus 400. Right? I mean, just think, if it's 3 negatives, that makes a negative, so it's minus 400. Wait a second. Yes. It kind of, in a way, relates a little bit to what we're doing here. It'll come up just a little bit if you pay attention. Okay. It'll all come out of your quiz time. You will take a quiz. If you have 5 minutes left, you will still take a quiz. What's your question? Projects? No. Okay. Okay, quiet please. You're going to slow us down, and you're going to get even less time for the quiz than you probably wish you had. Okay? So this is a really important topic, complex numbers. The objectives, which all come from the SOLs, take up 2 pages, right? Or 2 slides, at least the way that I did it, right? And so this is probably for almost everybody in here something you've never really presented with the concept before. So it makes all the more importance that you pay attention, think hard about it. I'm trying to make it as easy as I can, but in the end, it's something new to learn. You're not just regurgitating something that you had once before, right? It's probably the first time you've seen it. So it's better, I'll talk about these at the end, when everything ought to make a lot more sense by then. Okay. So this was a chart that we already saw, right? And it said that based on the value of the discriminant, then we knew whether or not we had 2 real answers, 1 real answer, or no real answers. Well, it's a little more complicated than that, because we usually don't say, and the objective actually does not say, just say how many real answers. If you actually look and see what the objective says, it says, is it there? No. Where is it? Well, solve a quadratic equation over the set of complex numbers using an appropriate strategy. So based on what we see here, we would not have been able to solve because we would have got a non-real answer. But that is not the end of the story, right? We have to keep going because there is another kind of number that we use to solve situations like this. Now, take, for example, this problem, which was number 25 in the homework. You were just asked, evaluate the discriminant, say how many answers that you would expect. And I did the whole quadratic formula with this. But you only did this part. But if you just follow it down, right, you should have gotten b squared minus 4ac was 4 squared minus 4 times 1 times 5, 16 minus 20, negative 4. That's what you got when you evaluated. Now, put that in your calculator, see what you get. What is the square root of negative 4? Right? If you put it in and you hit probably, not for sure, but probably, you're going to get an error, and it's going to say non-real, like that. Error, non-real. Okay? In order to actually solve this, we need to be able to, what is the one part of this that we're not able to do? Can we take the square root of 4? Yeah. Sure. It's the square root of the negative that you can't do. I mean, most of the time you would think, if every time if you're looking for a square is something, or the square root is something you multiply times itself to get the number, right? So a positive times a positive is a positive, and negative times a negative is a positive. How do you get a square that ends up being negative? Yeah. What's that? Sure. What is it? Okay. Is it going to be like a 2 square, but if you outside of it, no. No. Nothing wrong with guessing. He's thinking. Okay, so what we have to come up with now is how are we going to deal with the square root of a negative, or specifically, how are we going to come up with the square root of -1? That's something that we would say you can't do. In fact, what you do is you define the square root of -1. Right? You define the square root of -1 equal to this imaginary unit that they call it, represented by the lowercase letter I. And you can think of I for imaginary. Okay, I for imaginary. So now, when we get the square root of -1, we're not going to stop and say, non-real answer, can't do it. We're actually going to have to solve that. And we'll have I to be part of our answer. Okay, now, if you look at this, and this right here, this is the definition. You know, it's not the kind of thing you ask why. It's the kind of thing you just say, okay, that we're just defining the square root of -1 equals this letter I. And if you square both sides of that, then kind of goes hand in hand, you would get that -1 equals I squared. And we'll need that later on. When we're doing calculations with these numbers, every time we get an I squared, we'll replace it with a -1. Okay, so this is an important fact right here. So the definition of I and the fact that -1 equals I squared, those we're going to use. Yeah. Right. We're gonna get to that in a second. But just with this one definition, now that we have a way to handle the square root of a negative number, we go back to the problem that we were working on before, and we don't stop when we get the square root of -4. Instead, we say, well, the square root of 4 is 2, and the square root of -1 is I. All right, so we're not going to get a non-real answer, you know, an error that says non-real answer. You're actually going to get an answer. And notice, once I did that, then the 2 in the denominator divided into the 4 and divided into the 2, so it could be simplified as -2 plus or minus I. Here, the square root of 4. What's that? Well, what you really do is like this. You take the square root of 4, right? And you say that's going to be -1 times 4. The square root of -1 is I. The square root of 4 is 2. You break it up, if you simplify each part. So every time you get a negative inside a square root, you take it out as the letter I. Okay. Now, these numbers that have I in it, are called imaginary numbers. And it's kind of in a way unfortunate that we give it a title like that. But it's like you have real numbers and you have imaginary numbers, and you might think that the imaginary ones are just fake, kind of not for any real reason. But they really come up in math and science. And the one example that I can give you was when I was at Penn State studying for my bachelor's in meteorology, we had a class where we were studying, understand that the Earth is warmed by the sun, right? But the atmosphere is actually transparent to sunlight. And it takes some time for the sun to shine down and warm the Earth, and then for the Earth to warm the atmosphere. And for that reason, you don't get the hottest temperature of the day when you get the most direct sunshine. I mean, what time of day do you get the most direct sunshine? Noon or 1 o'clock in the summer because of the daylight savings time. But that's not when you get the hottest temperatures of the day. So there's some process going on. And we were trying to quantify, in a way, how long does it take between the max sunshine and the max temperature of the air. And so we modeled it with the kind of equations you use when you model the atmosphere, which are partial differential equations, things that you will get to about 5 courses down the road, right? And the solutions ended up involving I, right? They involved imaginary numbers. And the solution that we got, and this was just a model, and a lot of times when you do a mathematical model and you run it and you get an answer and it doesn't seem right. And so you know what you do? You go back to the drawing board and see, maybe I need a better model. But in this case, what we determined was it should be 1/8 of a cycle after the maximum sunshine, you should get the maximum temperature. So just think on a daily basis, what's 1/8 of a day? 3 hours. So if you get the maximum sunshine at noon, you would expect the maximum temperature at 3. Or in the summer, maximum sunshine at 1, maximum temperature at 4. Does it seem about right? Yeah, that's good. What about on a yearly basis? What day of the year do you get the most sunshine? Say again? The summer solstice, which is June 21st. But that's not when you get the hottest temperature of the year. What's 1/8 of a year? In months. 12 months divided by 8. 12 months divided by 8. 1.5 months. So go from the summer solstice, 1.5 months, about 6 weeks later, end of July, beginning of August. Does that seem about the right time for the hottest temperatures of the year? It does. So we had a mathematical model which led to imaginary numbers in the solution, which led to an answer that kind of squares with our intuition. We would not have thrown that model away and said back to the drawing board. It kind of seemed real. But it's actually involving imaginary numbers. And in math and science, they really do come up. Okay, they really do, even if we do call them imaginary. Okay, the big set of numbers. You probably up to this point thought, okay, the biggest set of numbers are real numbers. That's the big, all-inclusive set of numbers. That's not correct. The big set of numbers are called complex numbers. Complex numbers are all the real numbers plus all the imaginary numbers. Right? Complex numbers are written with this format. Is A plus BI, right? Where A and B are real numbers. So it means that there can be two parts to the complex number, right? One part that doesn't have an I in it, and one part that does. The part that doesn't have an I in it, that's real. The part that has an I in it, that's imaginary. And that is called standard form for a complex number, A plus BI. Now, real numbers are a subset of the complex numbers. If the B equals 0, then you don't have any I's. So all the numbers where B is 0, that's what the real numbers are, because there's no I. And if the B does not equal 0, then every number you've got has an I in it. Those are imaginary numbers. So we'll see it again when we go over those objectives that say at the very beginning, evaluate which properties hold for the complex numbers. That's the way the SOL is actually written. And by the properties, they mean all those properties we did on day 1. Commutative, distributive, all those things. They're specific about those applying to complex numbers. It's just that we don't get to complex numbers until we get to this lesson right here. That's why we cover them on the first day, kind of understanding. We're not going to get to it. The book doesn't even talk about the properties when they get to this section. Okay, so now we're going to go through the operations with complex numbers. And I've written it here using all letters, A plus BI plus or minus C plus DI. You might find it easier to look at the example where I'm adding 2 actual complex numbers. Right? The bottom line is, when you add or subtract complex numbers, you add or subtract the real parts, and you add or subtract the imaginary parts. You keep them separate. So in the example, if you're going to add 7 plus 3i plus 5 minus 4i, again, add the real parts. What are the real parts of those 2 numbers? The 7 plus the 5. right? So when you add the 7 plus the 5, you get 12. Then you're going to add the imaginary parts. All right, that'd be 3i. That's not right. 3i plus negative 4i equals, right, that'd be, it's kind of like adding like terms, right? You could think of the I like an X in this respect. We just add the coefficients, 3 minus 4 minus I. These? I just made it up. It's an example. It's just an example to practice what this says. This? Sometimes I take them from someplace, sometimes I make them up. Uh-huh. No, but we'll do that at the end, and you'll see. I mean, if you want to see when we solve the quadratic formula to solve a quadratic equation, and it leads to these things, we're going to get to that. That is kind of like the end of all of this. I mean, the truth is that's like the only thing we're really interested in here. But, you know, they introduce the complex numbers, and doing all the operations with complex numbers just becomes part of the lesson. Most of those you won't have much need to do at all, other than if they ask you a specific question like that. And they usually do. There's usually 2 or 3 questions that are just add or subtract complex numbers or something like that. Okay. How about this one that has 3 complex numbers? Yeah. So we still want to just keep the real parts together and the imaginary parts together. What are the real parts that we're adding here? 5 plus 3 minus 8, right? That's 5 plus 3 minus 8. That's the real part. And then what about the imaginary part? Yeah, we got to get our signs correct here, right? That's negative 3i plus 5i. And then what's the last one? Yeah. So this is negative 3i plus 5i minus 2i. And why is that a minus 2i? Because the negative in front of the parentheses, right? You got to take that into account. Okay, what is 5 plus 3 minus 8 is? 0. And negative 3i plus 5i minus 2i is 0i. So that's just 0. So, you know, when it talks about the field properties of complex numbers, if you go back to the properties that we did in day 1, again, if you look in the book, there's one property that we don't talk about a lot, but it's called closure property. Closure property says, you know, if you multiply 2 real numbers, you get a real number, right? You never go outside of the set. But you can see what happens, like if you said for imaginary numbers, can you add imaginary numbers and get a non-imaginary number? Yeah, I mean, we just did. We just added 3 imaginary numbers together, and we got a real number. So you don't have closure property. Yes? Well, I didn't. I simplified it. It's all 0. Okay? I just showing. So in the real part, we got a 0. In the imaginary part, we got a 0. We got a 0. Okay, so that's adding and subtracting complex numbers. Add real parts, add the imaginary parts, just like you add like terms, just like that. Okay, multiplying complex numbers. How do we normally multiply a binomial times a binomial? We usually say FOIL, right? And FOIL is what we're going to do here too, right? So we can say FOIL. All right, so let's see. The first term is going to be 2 times 3, which is 6. Okay. The next term, the outer terms, will be 2 times 3i. right? What do you think is 2 times 3i? It'll be 6i, right? And then the next term will be 3 times negative 4i. And then the last term will be negative 4i times positive 3i. Right? Okay, now let's simplify. Now let me do something first. Two times 3. Okay, so this is 6 plus 6i minus 12i. And then what about that last term? It's negative 4 times positive 3, which is negative 12. And then there's I times an I, which is I squared. But remember what we said on that first slide that had I in it. I squared equals negative 1. So we're going to say this is 6i minus 12i is minus 6i. And this is negative 12 times negative 1. Replace the I squared with negative 1. So this will be 6 minus 6i plus 12, which is 18 minus 6i. Right, since I is the square root of negative 1, I squared equals negative 1. So whenever we make an I squared through multiplication, we replace it with a negative 1. Right, how are we going to do the... Yeah. I can't hear you. Here? 3 times negative 4i. The inner. Right. So we had 6i minus 12i, 6i minus 12i, which is negative 6i. Negative 6i. Right. How are we going to do 4 plus 2i in parentheses squared? Write it twice, right? Write it like 4 plus 2i times 4 plus 2i. Okay? FOIL it. 16 plus 8i plus 8i plus 4i squared. Right? So you can add the I terms, right? 8i plus 8i. 16 plus 16i, and then 4i squared is minus 4, right? Because remember, 4 times negative 1. So now you can simplify. 16 minus 4 is 12. 12 plus 16i. So that is add, subtract, multiply. Yes. First, outer, inner, last. Just make sure you multiply everything in the first set of parentheses times everything in the last set of parentheses. You don't have to use FOIL. Okay. Now, there is a specific SOL requirement to understand the powers of I, right? So let's go through the pattern. It's just a pattern. It repeats itself all the time. And it's not that hard to learn, right? I to the first is I squared is negative 1. Those we've already dealt with, right? If you want to know I to the third would be I squared times I. But I squared is negative 1. So I to the third is actually negative I, right? It's the negative 1 comes from that, and the I comes from it, right? I to the fourth will be I squared times I squared. But I squared is negative 1. So negative 1 times negative 1, 1. Right? I to the fourth power equals 1. Okay. Now we'll go to I to the fifth, right? I to the fifth is I to the fourth times I. But I to the fourth is 1. So that's just I. Right? I to the sixth is I to the fourth times I squared. Right? Add the exponents. I to the fourth, that's 6 i's. But I to the fourth we just said is 1. So replace it with a 1, and I squared is negative 1. So that's 1 times negative 1, negative 1. Right? And we keep going. I to the seventh would be I to the fourth times I to the third. Well, there's I to the fourth, and there's I to the third. Negative I. I to the eighth is I to the fourth times I to the fourth. 1 times 1. So it's 1. So notice the pattern, right? Here was the 1, 2, 3, 4. I, negative 1. Negative I, positive 1. Right? Start over I to the fifth. I, negative 1. Negative I, positive 1. The same pattern, right? I mean, what would we expect if we had I to the ninth? It's 1 more than I to the eighth. Say again? It's I. Right? I to the 10th is 2 more than that. It's like the 6 was, negative 1. You just follow the pattern, right? Every 4 are in the same pattern exactly. I to the 11th would be I to the 8th times I to the 3rd. Negative I. And I to the 12th would be I to the 4th times I to the 4th times I to the 4th, which is 1. Same pattern. Every 4, they just repeat themselves. Okay? So what you know, right, is a pattern here. Every time you raise I to a multiple of 4, it's 1. Right? So just make it up. I to the 32nd, 1. Because 32 is a multiple of 4. Right? If you raise it to an even power, which is not a multiple of 4, it's negative 1. So I to the 50th. 50 is not divisible by 4, but it is a negative number, negative 1. Right? If it's 1 more than a multiple of 4, then it's going to be I. So I to the 49th is 1 more than 48, that's going to be I. If it's 1 less than a power of 4, then it'll be negative I. You should be able to figure out just from the pattern of those 4 numbers, right? 1, 2, 3, 4. Just repeat the pattern. I mean, for example, I to the 48th. Okay, I suggest that if you have to take, if it's so slow to take notes, go home, bring up the slides and the video, fill in what you didn't get, right? This is all coming out of your quiz time right now. Okay, let's see. So here's 4 powers of I. I to the 48. Let's see. 48 is a multiple of 4, so it should just be 1. Right? This is a, right, because 48 is a multiple of 4. Right? I to the 62nd. Is 62 a multiple of 4? But it's an even number. So, -1. Remember, just like we did on this one here. Right? For 2 is not a multiple of 4, but it's an even number. -1. Right? 6, -1. 10, -1. Yes. Even, but not multiple of 4. Okay, let's see. 4,001. 1 more than a multiple of 4. So it should be just I, right? Because the multiple of 4 itself is just 1. This is just 1 more I, right? So that's I, right? 1 more than multiple of 4, than multiple of 4. And then 3,999 would be 1 less. So it is -I. 1 less than a multiple of 4. So really, with any power of I, you should be able to just apply those rules. Okay. Now, we're familiar now with the complex number has a standard form of A plus BI. Right? When 2 complex numbers differ by only the sign in between, A plus BI, A minus BI, those are called conjugates. That's a vocabulary word, conjugates. Right? Now, if you multiply conjugates, notice what happens. Right? So here's my conjugates. I'm going to FOIL them. Right? The first, 4 times 4 is the first. That is 16. Right? The outer will be 4 times -5i. Right? The inner will be 4 times +5i. And the last will be 5i times -5i, which is -25i squared. Now, these two are opposite numbers, so you cancel them, right? -20i plus 20i. They're opposites. And that'll always be the case when you multiply conjugates, right? The 2 inner ones, the O and the I, will be opposites, and they cancel. And the last one has got that I squared in it. How are we going to deal with that? It's -1, right? So this is -25 times -1, which makes that a +25. So this is 16 plus 25. So we multiplied 2 imaginary numbers, and we got rid of all the imaginary parts of the numbers. Now we just got a real number. So that is a special case of when you multiply complex numbers. And we use this when we divide complex numbers, which is next, when you're ready. 16 plus 25. Yeah, negative 20i plus 20i. We done? Curtis? Good? So dividing, which is the one operation that we didn't do yet, actually uses this idea of multiplying conjugates, that when you do, you get rid of imaginary numbers. We really don't really say divide. It is kind of a divide. What we say is we simplify it so that this is in the form of a plus bi as a complex number. Right now, because it's being divided by an imaginary number, it's not in that form of a plus bi. So the strategy to turn that denominator into a real number so we can write in the form a plus bi is multiply the numerator and the denominator by the conjugate of the denominator. Right? It'll look like this. 4 plus 2i over 4 plus 2i. Right? Because what's going to happen when I multiply these in the denominator? They're conjugates, so all the i's are going to go away. So let's do that. In the denominator, this is going to be 4 minus 2i times 4 plus 2i. FOIL it. 4 times 4 is 16. 4 times 2i is 8i. 4 times negative 2i is negative 8i. And then the negative 2i times positive 2i is negative 4i squared. We're not done yet. Okay, we can see what's going to happen in the denominator, right? These 8i's are going to cancel. That's always going to happen. And then the last term, the I squared, is going to turn into a negative 1. So we won't have any more i's in the denominator. In the numerator, you still got to FOIL this. 2 times 4 is 8. 2 times 2i is 4i. 4 times 3i is 12i. And 3i times 2i, 6i squared. So let's see. In the numerator, we can do some simplifying, right? This will be 8 plus 16i minus 6. In the denominator, it will be 16 plus 4. Right? I added these two, 16i. These cancel. And then I substituted negative 1 for the I squareds. And then we could take one more step. 8 minus 6 is going to give us 2 plus 16i divided by 20. And that's not quite in the a plus bi form. Yes?
Okay. Wait, why is 4 plus 2i 4?
I multiplied by this to get rid of the imaginary numbers in the denominator. Because if I multiply like 2 minus 3i here to do it in the numerator, we need the denominator to be a real number, not the numerator. That's the way it works. Yes.
Oh,
okay. So now this here is not really in the form yet. You could split it up into two numbers, make it 2 over 20 plus 16 over 20 times I. And then each of those could be simplified. 2 over 20 is 1/10. And 16 over 20 is 4/5 times I. That is a plus bi, right? A plus bi. This is the answer. You know, why are we allowed to multiply by 4 plus 2i over 4 plus 2i? So why can I do that and not change the value? What is 4 plus 2i divided by 4 plus 2i? It's 1. So essentially all we're doing is multiplying times 1. You're allowed to do that. It doesn't change the value of anything. But by multiplying in this form, it's going to get rid of all the i's in the denominator so that we can write it as a plus bi complex number. Yes? When you're doubling them? When you're making an I squared? Here? Does it mean that everything's going to be positive? Not necessarily. Not necessarily. These could be negative. It could start with a negative 4. Doesn't have to be negative 4 minus 2i, negative 4 plus 2i. You'd end up with negative numbers. It's not always positive. Okay, finally, now that we know what complex and imaginary numbers are, we can solve quadratic equations that lead to imaginary solutions. And we don't just stop and say non-real answers. We follow it all the way through. So in a problem like this, I mean, most of the time when you get a quadratic equation to solve, you don't really know where it's going. My first thing when I look at it is to say, is it factorable? Because if it's factorable, I'm probably just going to factor it. 8 times 9 is 72. Are there any factors of 72 that add up to 14? No. So it's not factorable. You could try to graph it. You would probably see that it never crosses the x-axis. But the quadratic formula always works. So generally, you're just going to go to the quadratic formula at that point. I still have that on the board there, so I'm not going to rewrite the formula. I'm just going to fill in with A is 8, B is 14, C is 9. Right, so this will be x equals negative 14 plus or minus the square root of 14 squared minus 4 times 8 times 9 divided by 2 times 8. X equals negative 14 plus or minus the square root. 14 times 14 is 196. 4 times 8 times 9 minus 288, 16. So x equals negative 14 plus or minus the square root of 196 minus 288, negative 92. Now, is 92 a perfect square? No. So does it have any factors that are perfect squares? 4. 4 times 23. So if I simplify it like this, or I'll say the square root of negative 92, if I split that up into negative 4 times 23, like that, then I can simplify the first square root, right? The square root of negative 4 is 2i, right? So this is 2i times the square root of 23. So that's what we're going to replace right there. That'll be x equals, somebody got a phone or something? Plus or minus 2i times the square root of 23. Over 16. Okay? So you see where I just replaced this with this. And now what's the last step of simplifying I could do? You know, all of these numbers, 14 and 2 and 16, are all divisible by 2. So you could cancel a common factor of 2 in the numerator and the denominator. Right? Remember, that 23, which is in the radical, is never part of any canceling like that because it's in a radical. So this is negative 14 over 16 plus or minus 2i over, or sorry, I should say it like this. Usually the way you would write it is like this. where am I at? 2I times the square root of 23 over 16, which is negative 7 over 8 plus or minus 1 over 8. So that'll be I root 23 over 8. Okay. So if you go back to this table here, we really, at this step here, if we're really doing what the SOL requires, that at this point, we don't just say no real solutions, we say 2 imaginary solutions. When you get the discriminant is less than 0, you say 2 imaginary solutions. Which the new textbook kind of changed, because last year they actually they did imaginary numbers before the quadratic formula, so you never had to like go back like that. But this new textbook, they've kind of changed the way they did it. So now when we look at all these things, most of it's going to make sense, right? Recognize the square root of -1 is represented as I. Right? Determine the properties that apply to complex number system. It's mainly all the same ones that apply to real numbers, commutative, associative, all that stuff. Simplify radical expressions containing negative rational numbers and express in A plus BI form. Simplify powers of I. We did that. Add, subtract, and multiply complex numbers. Right? Understand, the hierarchy of the number sets, right? Complex being the big set of numbers, imaginary and real being subsets of that, rational, irrational, integers, whole, and natural are all real numbers. Write a real number in A plus BI form. Solve a quadratic equation over the set of complex numbers. Right. Those are all things that we pretty much touched on today. No, it's not on the quiz. It'll be on your next quiz. Those are the homeworks. So write them down, and we will get started on a quiz.